We can't hear you.
Can you hear me?
Yes.
Yeah.
All right. So we are very happy to have Juven Wang as our second speaker. He's from Harvard, CNSA, and he's going to tell us about modern effective field theory for fractional quantum Hall systems near nu equals 5/2 in 2 + 1 dimensions. Juven, take it away.
Okay, thank you. I feel embarrassed to show myself, so let me just say hi, and I don't have a photo, but let me go on with my talk without showing myself. Okay, so the talk will be on effective field theory (EFT) for fractional quantum Hall system near feeding fraction nu at 5/2 in 2 + 1D. This work is done with collaborations from Caltech, the team from Bosen Xin and Yinxuan Lin and Natalie Puckett, and based on this paper. And there's a prior work I done when I was IAS with Biaodian from Princeton University based on that. And I checked earlier, it seems like my collaborator was not online, but in any case, I still try to present. So in this talk, give you an abstract of what we'll be discussing. It's a model effective field theory in 2 + 1D. In a sense, it's a unified maybe effective field theory to describe some potent phase I will mention, and near feeding fraction 5/2. And this theory turned out to be Lorentz invariant and sit at an energy scale above the IR, such as topological field theory, TQFT descriptions, but below the UV completion, such as in condensed matter by electronic wave functions or on the lattice. However, I should mention the EFT we have actually is UV complete in the sense it's renormalizable. It's additional things, even though in condensed matter usually complete by electrons. And at low energy, it can produce a lot of IR phase appear in the previous work, such as non-abelian states, including Fabian, Maury state, and anti-Fabian particle conjugate states for Fabian. And also both of these are particle Hall symmetry breaking, and there's also particle Hall Fabian states. So we'll denote as this. There are also other abelian states I will touch as a k = 8 state or 113 states. We will show a phase diagram to relate all these 5 phases, and there is some more metal phase, another new phase, and also phase transitions. And we'll compare this phase diagram with the previously proposed percolating pictures in the disorder system I'll describe. And lastly, I will mention a one-loop Feynman diagram calculations from the EFT shows that compare the domain wall for the PF, APF domain wall compared with the domain wall in the PH Fabian state. It turns out that the former has larger energy than the later. So if a former of such a domain wall form in the disorder system, it may transient energetically to a favorite one of a PH Fabian domain wall. So this could in turn, we suggest, to help induce a bulk transition to PH Fabian. Okay, so any questions so far? And next, I'll go to detail, but there's a lot of historical work. I try to become enjoy more about history like Chen Ke, and but the history of the work of 5/2 is starting from here, 87. This non-abelian state was observed in experiment by this group, and Maury proposed the non-abelian Fabian, and there's people here, 2 groups propose a particle conjugate wave function for this anti-Fabian states, and their development of a topological insulator superconductor is T Fabian, and Demsong proposed this particle Fabian, and there was a reference. I received a complaint that it seems like this reference gives similar description for this state, but for the wave function, but without giving the same name. And Zucker and Feldman also write down PH Fabian wave functions. While the later part of my talk will start from this reference of describing the disorder percolating induced phases and how it's relevant for new 5/2. So I will not mention most of the reference again in the next. Please interrupt me if there's any question. Okay, so the system we'll look at, the universe we'll look at is just something living a sample in the lab, apply strong magnetic field, measure the current and voltage, and tuning the Tesla, in magnetic field in Tesla, you have some kind of a measurement of resistivity, RXX, along this direction XX and also the RXY. And the state we will look at is actually a filling fraction phi half with a quantum hole of phi half. So the resistivity should be 2/5. And also the sigma axis need to be 0. So there's a bulk gap and Rx is 0. So the state we should look at is somewhere between this label between 2 and 3, somewhere here. So this table 432 is the two filling fractions. But it's not clear that there's no plateau, obvious plateau at the phi half, and there is no sigma x go to 0. So we should zoom in. So zoom into the box and zoom in further. So these are experiments done. People find that indeed there's a phi halves. There's a like plateau for xy, and there's a dips. But the temperature may not be low enough. But presumably, if you lower the temperature, you will really see a more clear plateau and this type of dip for Rx. So this Rxy is blue, Rx is in green. So we will consider a universe living in this sample around this magnetic field applied, such that the filling fraction is such. And the whole conductance will be phi half always in my talk. Okay. So once we have this data, we need a few more data. There's another data important. It's recently done by 2017 by this group. These are the real data in experiments. So thermal hole conductance measured to be filling fraction phi half. Turns out is shown here in this figure. Horizontal axis temperature in millikelvin. Vertical axis is kappa, which is thermal hole conductance. For field series, you should know this is relevant for the age states in 1+1D for the 2+1D bulk, which is chiral central charge, Cl minus Cr. And this turned out to be close to 2.5, which is phi half. And for the filling fraction around phi half is thermal hole is phi half. So sigma xy is phi half, thermal hole is phi half. So there's actually a puzzle. Experiments show this data while numerics try to simulate such a ground state. It turns out that they show that Fabian or anti-Fabian are preferred, and with the same electric hole conductance, but different thermal hole, so different central charge. So there's a conflict or dilemma. So this motivates the work later. But before I try to go to that work, let me take you for vocations. So May is the mother month for the mother state, and we want to give mother special vacations in summer, even though we are in the lockdown time. So let's try to go to a Pacific Ocean with sunshine like this. It's archipelago, where you see the green and the blue area. The green is like islands or the land, the blue is sea or oceans. If you go to this place, sometimes you don't know whether the land are dominant or the sea are dominant. Are you really on the land or you are in the ocean? So that's a question. So I'll call this a sample of a Fabian anti-Fabian system. So what really you expect in that universe of that sample is that if you zoom in, you'll find out a lot of land dominant, perhaps, but there is still some kind of puddle of the other side, the other kind of order. So the order of the one kind can be, for example, a Fabian, such as the one I draw as land or island, depends on dominance, and also sea or ocean in contrast. So you can imagine one of the regions such as this, the one I draw the dominant here can be Fabian state, it's a land. And here the sea level is low. While in the horizontal axis, you are tuning the sea level, such a sea level increase, and as if the filling fraction in that analogy is increasing and tuned by magnetic field. So when sea level is low, land is dominant, and this could be a Fabian state. While you measure the kappa xy, is measure the age degree of freedom. It turns out that the age degree of freedom is captured by Fabian, and which can be some of the value. Schematically, I only show one of the 1/2 phase. For example, like chiral P wave superconductors, 1/2 with Marana vial fermion in 1+1D. But I will go to a Fabian state in real. But right now, just give a simple example. While the sea level increased to a certain percolating, so-called percolating transition point, that the land become sea can become hardly distinguishable which one is dominance, then this will be a transition point. And tune further, the sea will increase, so you'll see the ocean and then just some few isolated lands. Then you see more of the sea and dominant by another phase, another type of order, for example, kappa is at 0. For the Fabian system, we need to change that to a kappa xy to 7/2. and the anti-Fabian state will be 3/2. So the latency will be dominated by either way. And what you see on this puddle with this boundary called the 1+1 domain wall or edge theory will have a 4 Marana vial fermions in 1+1D, which has 4 times 1/2 central charge is 2. So the central charge on this island can be measured, should be 2 if it's measurable. But what will be happening is that if I tune the Billing fraction at sea level to this percolating transition point, you will see that after the critical point, the order will change, and the edge on this percolating this puddle will touch the edge and then changing the central charge. So that's basically a rough idea how the transition might happen. Okay, so these are a way to imagine what the sample will look like in the lab and when tuning the Billing fraction near 5/2. But it's not yet enough to explain what the puzzle can be resolved. And there are further calculations we need to do to thinking about this, what happened in 1+1 DCFT on this domain. And there should be some scattering and random effects and to take care. In the previous work I done with Biao Lian, I think in the audience, suggests a possible phase diagram like this, such that there are certain energy scale in the vertical axis is called the disorder straits, while the horizontal axis is the Billing fraction. So when the Billing fraction is near 5/2, called nu C, it could be shifted, not exactly 5/2, but it should be near 5/2. And this disorder energy is like horizontal vertical axis. There are 2 energy scale. We find that when lambda 1 energy scale, when energy disorder scale roughly captured by this inverse size of the linear size of the puddle. So more puddle, more disorder. So we find that there's a scale, say lambda 1. Below the lambda 1 scale, there's an emergent symmetry for the edge. It's emergent, so it's not exact. It's just a perturbative analysis done by RG, consider some scattering process of something like this type. And short of time, so I just give you a result. There's an awful symmetry below lambda 1. Well, there's an energy scale lambda 2 such that the energy, the emergent symmetry will be different. It's O2 times O2. And what it suggests is that below the lambda 1 scale, the 4 Marana running on the puddle will bond together. So when they try to go through the percolating transition, they will go through together. So central charge can be drawn by 4 times 1/2, which is 2. So this is how Fabian change anti-Fabian goes through that transition. However, if you are above the disorder energy of lambda 1 and below lambda 2, there's O2 times O2 emergent symmetry for 4 Marana. So 2 of the Marana bound together. That means the central charge may jump by 1, but the other jump may not need to be the same transition. So that's why there could be a 5/2 above lambda 1, but not below lambda 1, because the reasoning of the emergent symmetry. If further increase the symmetry, increase the disorder energy scale below lambda 2, the all emergent symmetry seem to break and to only fermion parity. In that case, the 4 Marana running on this domain of a puddle does not need to transcend through this percolating transition at the same point, same transition point. So you can imagine there are 4 discrete, 4 separate transitions. Each time jump 1/2, 1/2. So that's why the 7/2 can jump to 3, which turned out to be possible abundant state, and to 5/2, to 2, to 3/2. So that's a rough idea of that picture. Any questions so far? So the goal will be the EFT. The question I will ask is that, is there some kind of effective field state description to capture the phase and phase transitions? Okay, and if I draw, in case if anything unclear, please let me know. If I draw more physical observable data such as thermal conductance, and in the vertical axis, kappa xy, and horizontal axis is Billing fractions, nu, and near the nu C, 5/2. If we change the disorder straits, suppose we can change a different sample and do a measurement again, then you see the nu, this kappa xy will jump from 7/2 to 3/2. These are just schematic like this, which means from Fabian PF to APF, anti-Fabian. Well, if I go to an energy scale between lambda 1 and lambda 2, as I say, there could be a jump, and such the jump may be more smoother due to a finite disorder, and then go to a plateau of 5 half, and then go to a 3 half again. Okay, and if I further increase disorder, then there's a separate 4 jumps from 7 half to 3 to 5 half, and then to 2 to 3 half. So these are the solid line. And furthermore, if I increase more, there could be even smooth kappa xy. And if we imagine such things is there, we can also ask what the kappa xx. It turns out that such a state have a kappa axis may diverge at the temperature. So this means these are metallic-like state, and it's a so-called thermal metal with unquantized kappa xy, but large or diverge kappa axis at a low temperature. So that phase are quite distinct from the TQFT phases, presumably for those plateau, which has quantized kappa xy, but the kappa xx is 0. Okay, so worthwhile mentioning, 2 other groups produce different type of phase diagram. For example, Morose, Stern et al. They consider from the Weissman, and they consider the same question. And then at the near new C and also this 0 disorder, there's a unique first order transition, which I'll mention more later. Well, there's a separate 4 distinct transitions at finite disorder. And the Harvard's group, they produce a phase diagram similar to this type. Well, they mentioned the thermal metal might dominant somewhere, and that can be understand the broadening region drawn in this plot. So this region shows unquantized kappa xy can be understood as a broadening, such a transition as from the shop can become a more broadened, a smooth region. So if that smooth region become even wider, they could connect to the thermal metal phase at the top, connect to a thermal metal phase at the top. Okay, so that's basically the previous setup. So there's the issues. So previous population picture rely on 1+1 Ig theory analysis and shows possible transition, but it does not uniquely determine the 2+1 bulk TQFT order. So also the energetics of PF, APF domain wall compared to pH Fabian phases and their domain wall are not clear. And there's no much analytic analysis. Maybe there are some numerical works, but we are lack of a unified bulk description for this White state. So the goal is that we would like to write down a 2+1D EFT. Furthermore, we want to do the energetic analysis for the Fabian once we have this EFT and compute the tension. And this computation requires some classical and one loop and some additional calculations mentioned later. Okay. So just go back to the phase diagram. So there was the schematic from this 1+1DH, but furthermore, to set up stage, I should mention that if we expect such a state indeed are some abelian state, TQFT, K2A, 113, or non-abelian, these 3 states, we should be able to write down a TQFT unambiguously as native or like. So we will write it down in the precise way. And there are 2 expressions. One on the bottom is something probably more familiar to people like Max. And another expression is will be used mostly in our work. Is the orthogonal gauge group O2 Chern-Simons theory with 2 levels. First level is the like a U1 level, SO2 level. A second level is the Z2, a discrete Z2 level. Okay, and that level turn out to have a ZA class, and I will describe. And once one try to write down this TQFT precisely, then we can ask, can we produce a EFT to produce all these 5 phases and their possible phase transition, describe them, and also the thermal metal phases. So these are the universe we want to describe in this small sample. Okay. And as I also comment, because there could be a broadening due to finite disorder, and the broadening could be increasing as the disorder getting strong. So this broadening could become smoother, smooth the thermal hole, kappa xy. And that idea can connect to what the Wang et al. Proposed on the phase diagram, in the sense that you can thinking about this phase diagram at a certain limit will produce other people's phase diagram. So we will just focus on this type and thinking about how do we describe the phases here. Okay. Okay, so let me comment more later. Once I have an EFT, we can comment. So to give out the data, so just tell you that they are reference, including work by Nati et al. And we can write down certain 2+1D ZA class of TQFT they obtained from Bordizan group, they classify actually fermionic SPT protected by Z2 on-site and Z2 fermion parity symmetry. They are ZA class. Once you gauge the Z2 on-site symmetry, they are A class of the fermionic TQFT, a spin TQFT, because fermionic parity is still ungauged, only gauges Z2. So they are ZA class of a Z2 discrete gauge theory. The R class in the ZA 1, 3, 5, 7 are non-abelian. The other 4 is abelian, and we will need some of them. And we will also write them in terms of O2 gauge theory in this way, which is U1 level A and times so-called TL phase. L is in ZA, 8 of the class, and model Z2 of gauge group. And this can be understood from condensed matter point of view by project out some of the anyons on U1 level A and TL, and also identify some of the line operator. But by the recent modern language of the generalized global symmetry, we can view this as identify the certain one-phone Z2 symmetry charge line operator from U1 level A and or TL, and such identify line operator, and also symmetry generator. So this will reduce the line operator spectrums, and which means that we will reduce the anyons and quasi-particle quasi-holes for the theory. Okay. So in our paper, we also describe not just TQFT, but also wave functions. And if you are not familiar, I think the appendix can review all these materials in one single paper. Okay, but once we have that data, we want to pack them into the form. So the first form is something probably condensed matter people usually use, and we will write down in this way. And there's a conversion of the relation between them. And one thing you will ask what the experimental list can measure is the chiral charge, which is thermal hole conductance. And that can be counted by the level of O2 level 2, 1 transassignment. The level U1 level A contribute chiral central charge 1. The other sector actually has chiral anti-chiral modes, so it doesn't contribute central charge. So it contributes central charge 1 for the first part. So all this sector contributes central charge 1. Gravitational transassignment theory is kind of like counter term. This will contribute a 1 single chiral Marana vial fermions, central charge 1/2. And 5 of them contribute 5/2. So 1 plus 5/2 will be 7/2, and etc. 1 plus 4/2 will be, you know the answer, 6. And then all this number can be produced. So we would like to write down EFT relay them in the theory. Okay. So the EFT contain this transassignment I described, a non-abelian one, but also 4 Marana need to introduce with discrete charge conjugation gauge field. That is the Z2 in the O2. And that Z2 is SO2 semi-array R times Z2C, it's curl C. But this Z2C is identified with the fermion parity of big F of the 4 Marana, and both are identified engaged. We will need to also introduce the Yukawa Higgs field and couple to the Dirac fermions or Marana fermion by this Gross-Navier type. So these are the new terms we will write down. Via the deformation including Higgs and the potential and the fermionic mass terms, we will map out the phase diagram and then compare with the previous proposed diagram, phase diagram. So the first sector for the part 1 of this EFT will be as simple as possible. So just write down this TQFT sector, which contributes central charge 5/2 and still filling fraction 5/2. So there should be appropriate coupling to the electromagnetic A gauge field. I will skip, no time to describe in 30 minutes. But then I will still be mentioning the key features line by line. So the additional sector will be Gross-Navier Yukawa term, 2 flavor of Dirac, and can be also written as 2 Maranas for each. So they are 4 Marana. Okay, and there's a mass term we introduce for the convenience. We're choosing a sign like this way, and the Higgs potential will be standard. And importantly, this phi is in real value, and that's the setup. So all these 5 things add together will be the first part of EFT, which will help us to map out part of a phase diagram. And I think Nati will challenge us, and also in his very nice email to say that we should be careful about the symmetry, and as we should. So we should say that the big fermion parity F is gauged, which is the fermion parity in the this Marana fermion sector, and that's Z2 big F identifies Z2 curl C, and that's the same as the Z2 gauge field in O2. There's another charge conjugation we didn't touch, and that's the usual one in this Dirac fermion. So I use the normal C, the italic C. Well, there is also a Z-fold time reversal CT, or so-called particle pH symmetry, where CT square is -1 F, but this F is a little f, it's a different F, and such that these are the fermion parity still remain in the whole system. And what it will really act, you can imagine, is in this fermionic topological order, or the spin TQ of T in this 2+1D, this sector. But the time reversal action will be like this, such that T square, CT square -1. And it will also act on this Higgs field, such that it will be like pseudo scatter. So phi will flip side to -phi on the CT. So this is all the way we define time reversal, or CT pH symmetry. And this will be a quick way to maybe answer also Nati's question, is that we can also regard the gauging the way we say as the following: write down this O2 2,1 transassignments, and with this identification of the Z2C from the O2 and Z2F, and this need to be gauged. But we can also start from the SO2 level 2 transassignments, and which is just U1 level 2, and with gross W Kawa. And then we need to add some fermionic SPT with 2 over Z2 symmetry. One of them is remain ungauged, the little f. The other big F will gauge. And such that gauging the Z2 big F and identify with Z2 curl C, and then we will get the T curve T we want. So the symmetry, there are many discrete symmetry. I think I don't have time, so let me just list them, and then maybe I can share a slide to you if you have interest. And furthermore, the global symmetry for EFT can be analyzed. If I have a no Dirac mass, which if M is 0, then the formula has the 0 mass, they can rotate. So there should be an O-fold. But part of the Z2 sitting inside SO2, and which is a fermion Z2 big F, that's gauged, so need to model. If I tune on non-trivial, non-zero mass and have a Dirac mass and with different sign, they break this global symmetry to O2 times O2, but again, part of the Z2 is gauged. So these are questions field theories will ask. But for people like Xiaogang and condensed matter theorists may want to know what kind of gapless phase transition can describe. So it will be, I think, it will be similar to semi-metal-like probably phase transition, because we have isolated gapless nodes, like formula in our case. We don't have a metallic-like Fermi surface. So just from this EFT point of view. So that's a brief comment. But I haven't really get anywhere to get the producer phase. So, but it's become closer once I introduce the Higgs. This preserves CT in Lagrangian and action, but it will be CT will be spontaneous broken in a sense. Once this has non-trivial VAF due to the mu, appropriate mu and lambda, so the potential look like this. So there are two VAF. Phi horizontal axis can take value -V and V, and the potential look like this V phi. If we consider the mass of the Dirac M is 0, then we can see the Dirac mass from M, from the Bayer mass is 0, but it has contribution from the Higgs term, because we have a Yukawa Higgs term. So it will shift the mass of Dirac M1 and M2. Suppose M is 0, they will shift in the same way. And depends on the phi VAF, it's -V or +V, the fermion mass sign is different. And we can integrate those massive fermion. If the mass is negative, it turns out that we can produce Fabian states where the level and the gravitational transassignment term will be shifted due to that there will be additional 1+1D edge modes. And similarly, if phi is V larger than 0, we get different TQFT order called anti-Fabian. And the difference between the two should be the mass, 2 of the mass contribution from the Dirac fermion from negative large to positive large, and which is exactly Carlson charge 2. On the other hand, suppose I tune on the mass to be large than this GV. So the Dirac mass M1 and M2 share the same opposite sign, sorry. So when M is larger than absolute value or G phi, which take, so the Dirac mass has the opposite sign. When we integrate our two opposite side Dirac fermion mass, actually we don't get additional contribution. So this go to the pH Fabian. I should mention that the CT symmetry will be spontaneous broken once the theory live on this VAF. So the Fabian anti-Fabian will break CT symmetry. Well, pH Fabian in this setting, if the VAF look like this, will also break CT. But we can imagine that if the mu square, suppose the mu square can change sign near such a critical GV, and there's a relation between M and GV. When the M larger than GV, the mu square also changes sign. We can also flip the potential. So we can possibly go to a CT invariant, pH invariant, pH Fabian state as a single VAP. However, I want to mention such a setting like with two VAP, with Fabian, anti-Fabian, and pH Fabian, breaking the CT with a domain wall will be useful for the later calculation we need to analyze energetic of a domain wall in a 1+1D domain wall between the 2+1D VAP of different CT breaking theory. So we will analyze the domain wall living between such two VAPs later. Okay. Any question? So if I do the information, combine the information, I get a phase diagram. We get a phase diagram like this. These are the axes we tune the mass M. We would like to imagine such mass parameter with radial disorder. It will be more clear later. And if so, then along this vertical axis like disorder, indeed, at a larger disorder, we get pH Fabian. By the small disorder below this VAF value, M is smaller than GV, either depends on the symmetry breaking pattern. It can be Fabian or anti-Fabian. But in order to really go to Fabian, anti-Fabian, we should introduce additional horizontal axis. So this axis will be a second part by adding a potential by a linear term. And this linear potential is like applied magnetic field. And it will break CT explicitly. Other ingredients are the same. Okay. And it will change the Dirac mass M1, M2 by also shifting this odd power VAF value. So the potential will be tilted so that either Fabian will be preferred at phi smaller than V, or anti-Fabian will be preferred when phi is larger than V. So this will produce a phase diagram like this, as you can imagine. So when MR is small than 0, there's Fabian and vice versa. And we can determine a critical line analytically, depends on the modeling of the theory, map out this precise analytical critical lines when the Dirac mass change sign, and the phase diagram looks like this. And certainly, there are details of the EFT. We cannot, other than just manually just give this potential. But once you have this EFT, everything should be computable. Okay, and the last sector we want to introduce the Marana mass term. And this will split further the critical line. And such a Marana mass term have these effects we want. And the way to do this is that imagine such a mass can be introduced at some scale around or above this GV, and such that this value also is small. And this small value can split the critical line into two critical lines. So instead of just single Marana, single Dirac fermion change sign, the two Marana can change sign at a different critical line. And if so, you can imagine we can produce all the TQ of this sector. And lastly, I'm still lacking the thermal metal phases. We can introduce that by thinking this M has some randomness as a Gaussian distribution around the M I'm tuning, but there's a fluctuation like there's a Gaussian distribution we call delta, let's say. This delta can be a function and increasing as the M disorder stress increasing. When such a disorder increasing, you can imagine this critical line also become a broadening. And these are based on the previous knowledge from condensed matter community. There should be a broadening. And if we have that and the broadening become wider and wider, and we'll produce a phase diagram schematically like this, the thermal metal will be unquantized. Okay, and there will be a broadening. Okay. So I should mention that the transition at this breaking CT breaking should be first order as a VAF jump, but above, based on the model we have, can be first order transitions all along this line. However, if there's a broadening, the common knowledge is that the broadening will change the first order to a region that's thermal hole conductance unquantized. And if so, you may ask, can it be a crossover? And the answer is no, because on two sides are two different TQFT, so two different topological order. They cannot be a crossover. They should be a topological phase transitions. And that phase transition can be a second order transition somewhere sitting inside the broadening region. And in our EFT, on the other hand, can produce second order transitions just based on tuning the mass. You can imagine this can be a second order transitions. And here, if we add the effect of a fluctuating mass, you can imagine the first order transition may change to second order. well, this point at the zero disorder should be first order transition. So first order and above somewhere can be second order and all second order. And the thermal metal transition will be second order transition, a continuous space transition, like the metal insulator transition. Okay, so finally, as I mentioned, the global symmetry, there's something you should distinguish is that the global symmetry of analysis in previous 1+1D age are certainly distinct from the 2+1D EFT global symmetry. And I just list them because actually the system look at different, the dimension is different, the theory is different, but there are some relation and it may be worthwhile to think more. Also the MR will explicitly break CT. Okay. So the EFT capture known features of also this gap domain wall of this Fabian anti-Fabian. So we want to do this energetic analysis. We find actually a pH Fabian has low energy. And if that forms, we want to suggest that the pH Fabian domain wall, suppose there's a Fabian anti-Fabian domain wall, and then we analyze energetics. It turns out the pH Fabian domain wall has low energy. So if such domain wall form in the sample, it may go to a pH Fabian domain wall. And that domain wall has CT breaking on this potential CT breaking. But we want to suggest perhaps it can further induce the bulk transition to pH Fabian. And how do you see that? So first, the calculation done in the paper is that suppose we tune the mass, which is associated to some kind of disorder we expect. Below this critical depth GV, we say is Fabian or anti-Fabian, and we can analyze domain wall in 1+1D. And above is pH Fabian with CT break different depth. We analyze domain wall between the two, and these heroic calculations are done by Natalie and Yinxuan. They suggest the schematic curve look like this. And what you will expect is that the tension indeed decrease. Tension values evaluate by consider the action and evaluate the area and the tension. And there's some one loop calculation we need to do for consider the fermions. There are some fermions we introduce, and they can couple to through Yukawa Higgs term to this scalar modes, and then we'll have effects of renormalizations. And there are details. These are very technical, so I will skip. But the result is that the tension seems decreased, and the numerical data are real ones like this, where W is a rescale mass, like this mass M, so which we expect to be something like disorder. While the several color curve is just some coupling of Yukawa renormalized, rescaled Yukawa coupling. But regardless of any Yukawa coupling, you'll find that in the Fabian anti-Fabian has higher tension, and pH Fabian domain wall has a lower tension, and then monotonic decrease. Okay, so let me end the talk. So I have described a 5-Hall system, and with the EFT as a parent EFT, and such that there is a Grosvenor Yukawa sector engaged appropriately by identifying some discrete symmetry, and with non-abelian O2 gauge group. There's a more careful analysis about global symmetries, and I briefly describe. The Fabian anti-Fabian domain wall indeed are energetically less favor compared to pH Fabian domain wall, so there could be a induced transition go to the other one. And lastly, connect to the talk of Yunqin is that we always ponder this symmetry as emergent or spontaneous symmetry or breaking or emergent symmetry, like the QCD theory, QCD4. In a low energy, we have a chiral symmetry breaking, so the symmetry is lower. When we increase the temperature in this quark-gluon plasma, the symmetry might restore. And similarly, for the most condensed matter system like ferromagnet superfluid, low T has spontaneous symmetry breaking, so small symmetry. And this motivate work by Zoha et al. To find out whether they are counterexample. But to bring your attention is that in this 5-Hall system, if we regard this order as some kind of energy scale, although it's not temperature, but when we lower this order, we may have a larger emergent symmetry. And these are maybe interesting. Well, thank you for staying tuned.
Thank you so much, Juven. For now, we have maybe 1 minute for a very quick question, if there is any.
Yuan,
Yes.
can you explain? I don't understand the domain wall between pH Fabian and pH Fabian. What is that domain wall?
Right. So that's something I mentioned earlier here. So suppose I have EFT, like what we write, and suppose we have a Higgs potential. In the region when we tune such a so-called disorder that we associate with some mass, and below that m small or m below this VAV value, there are two VAV, and two VAV actually has two same side of the raw mass, integral get Fabian, anti-Fabian. And this phi, a two VAV will break CT because the CT symmetry in our definition flip phi 2 minus phi. And the question you ask will be, how about pH Fabian? And that's a bit bizarre because pH Fabian we expect preserve CT. But in a way, we could got the pH Fabian can also be depends on the sign of this mu square potential. So I'm just consider what the mu square is opposite side. In the way I write, it's actually the same side, just mu square lambda produce this potential. Then these two VAV actually break CT, and they are conjugate, pH conjugate to each other. However, our EFT certainly have degree of freedom or maybe other microscopic reason to tune the mu, such that mu might flip side. So in the usual case, I suppose Dan will be thinking this the V phi will be just go something like this. So there's a single VAV and CT is preserved. But just for the purpose of calculating the domain wall, also in pH Fabian, we imagine it could be a two VAV and there's the CT breaking domain wall. I don't know whether this answers your question. So we do this calculation. Yeah. And but this may be not natural just from CT preserving point of view. If you imagine mu square somehow flip side so that at the scale m is around GV, the mu square face side, some Landau Ginsburg like theory, then it could just be a CT preserving that. Yeah. But in case that that scale, you don't want to have a fine tuning, so the scale is exactly hit here, right? So suppose it's around, you can imagine even if it's above, so there's still a region CT might be breaking below that scale where mu square flip side, but above GV, GV is too small. So M is larger than GV, but smaller than mu square flip side. There's a region such that pH Fabian might still form a domain wall. And the calculation we did may suggest the following. Along that region, yeah, maybe this figure is good. Along this region, also some scale like here, along that region, even pH Fabian might form a domain wall, and with CT spontaneous breaking, they may restore. So there will be additional story. So first, PF Fabian and H Fabian form a domain wall, which both CT breaking, but energetically go to a pH Fabian domain wall, such CT still spontaneous breaking. But the pH Fabian is the same order, and if it fluctuate, perhaps CT restore. That's a same combination of the microscopic picture in the population and also the more intermediate field theory at the intermediate energy. Yeah, and then probably the scales suggest several energy scale. And EFT has a degree to tune, and there could be a better microscopic understanding to help. Yeah.
Thank you.
Thank you.
In the case where you have a second order transition, do you know anything about this conformal field theory at that point? Is it the conformal field theory that we know about from other places?
A very good question. We don't know yet. So there are still many things, still not satisfactory, but at least but it's on the table, so one can study. And also there are so many energy scale, we don't have a very good reasoning why we need to do this way. As I say, I show like 3 different phase diagram, and I think this EFT can produce all different 3. Depends on how we set each of a scale.
Nope.
And yeah. So, and then, as you say, for the critical line, these are second order, yes. And is there a CFT description? We haven't done that. Yeah.
Well, if it is critical, there should better be a CFT there.
Yeah, indeed. Maybe if Boshan is here, I don't know he's here. Maybe
I also have another question. Is there a general argument a priori why a single continuum field theory should capture the entire phase diagram rather than different field theories capturing different portions of it.
That's true. Not sure. Well, I guess we are the person who want to have some unification. So it's good to have a single theory than have 5 different, right? So if we can describe all by a EFT, then maybe it's maybe how do you say, aesthetically is better. Well, that requires some microscopy understanding too. So I couldn't just say that, but yeah. So it could also be other way. Maybe the 5-phase can be different theory. Yeah, but in the language, you always like to comment. Condensed matter people like to say, oh, all the phase live in the same sample, so they share the same Hilbert space. And you have that conjecture say that if the theory has same Tahoe anomalies, then there should be a way to deform them by a deformation of quantum field theory you mentioned. So it's good to think that way. So there should be a QFT to connect all the 5. You know, there's a deformation of the QFT that you introduce.
Juven, I kind of have the opposite question. Why should there be any continuum field theory that describes the physics of this, the same physics as this picture with archipelagos that you described? Yeah.
Well, so that's a relation between how the microscopy theory at the higher energy scale has something to do with EFT we write down. It's not entirely clear yet because, as I mentioned, the disorder stress is lambda. There has a microscopy picture like the inverse size of a puddle, but the M is just some Dirac mass we introduce. So that's really bizarre. How the Dirac mass we introduce as M has something to do with disorder stress lambda. And at some point I was wondering, has that something to do with disorder can generate a mass, like a symmetry mass generation? Maybe along that line can answer your question. Yeah, but the answer is not clear. I just say that perhaps symmetry mass from disorder can generate some kind of mass like this. So that could be a rewriting of this M by something else. And so they may relate the microscopy or percolation of archipelago to this lambda to the M in this picture. Yeah, but not clear. But there are some thoughts.
Can I comment on that? So yeah, I don't like your identifying mass with disorder strength because you have this percolation transition, which is some complicated, even for the integer quantum Hall effect, describing that transition is an extremely complicated business, which hasn't been fully solved. But the way I think I would interpret your calculation is that it's giving you some parent field theory, which gives you, by varying a mass, you can go to different topological phases. And what you can use your field theory for is to estimate the energy of a single domain wall. But I'm not sure you can use it for much else.
Mm-hmm.
I mean,
yeah, maybe I can.
That sense, you can take your field theory and build a domain wall and get some energetics for it, or other properties of domain wall. But I don't think you can make statements about the fully disordered problem.
Subir, can you explain why you think
could you explain why it should capture the domain wall energetics even?
It could. It's some theory that has the right boundary conditions anyway.
Typically, the domain wall is more sensitive to higher energy physics than the low energy field theory. So if an irrelevant operator in the field theory that would not be important to describe the transition could be important to describe the properties of the domain wall.
Is there a question? Sorry.
Well, it's a question for Subir actually, because
I was trying to be, I think we don't know what this theory has a UV physics which is totally different from the actual electrons for sure. So who knows what the energy of a domain wall in the actual electronic system is? But this is one theory that can at least get one and get you some systematics. Yeah, I agree with you though.
I think maybe there's another way to interpret the phase diagram if we go back to the previous slides. So I also agree that it's not very natural to associate disorder strength with mass. But I think there's another possibility associating disorder strength to the interaction, fermion interaction, I mean the mass-mass interaction, such that by tuning the parameter, you can drive the condensation of this mass term. So that requires a finite strength of interaction strength. So that could possibly as well produce this phase diagram, but then this spontaneous symmetry, pH symmetry breaking line is no longer a first order transition, but becomes a second order transition with O4 emergent symmetry. So that's another alternative story that might better match the previous 1D analysis, I think. And it's also more natural to think of disorder may, for example, you integrate out all this disorder configuration that mediates certain fermion bilinear interaction, which is this mass-mass interaction.
Yes, thanks, Yizhong, for the comments. Thank you for speak up. I'm glad you speak up.
All right, if there is no other comment or question, let's thank both speakers again, Juven and Yunchen. So our next meeting will be on June 10th. And as you may have noticed, we put a pause on our biweekly meetings as there are other UQM events, such as the one coming up the first week of June. All right, thanks everyone for joining us today, and hope you stay safe and healthy. Thanks.
Thank you, Hassan. Thank you, everyone.
Thank you.